Hello, everybody. Okay, so let's just continue from where we left off in the last class. We spoke about the tungsten filament, which is a thermionic emission, which emits electrons by the process of thermionic emission. And now we're going to get into what is a field emission gun. So the field emission gun essentially works by implementing the process of quantum tunneling. Okay. Um, Quantum tunneling is a process that is used for various other applications, for scanning, tunneling, electron microscopy, um, and I don't want to get into the details of the quantum mechanics involved, but maybe provide with a classical picture where you can understand what quantum tunneling is all about. So again, I'm going to do a classical treatment to get an understanding of what's going on. Okay. So let's just work out the math so that it's easier for you to understand. So we learned in the previous class that the thermionic emission, it can be expressed by the Richardson-Dushman equation, which is 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 A times T squared and then an exponential term, right? So this is your Richardson constant, which is material dependent. And then T is the operating temperature of the filament, and phi is the work function. Okay, so now if you look at this is your thermionic current. So in this relationship, you see that the thermionic current is completely independent of the potential that is applied to the anode. Yes, with the anode is, just for a reminder, that's the electrode to which you apply the tens of kilovolts to accelerate the electrons, which means if you increase the potential in the anode, if you go just by this equation, then the thermionic current should not be affected at all, because you don't see the anode potential in this equation, right? But turns out that this is not true. And it was in 1914 when Schottky found out that if you were to plot the anode potential as a function of the thermionic current, then there is always a slight increase, and it is not completely independent of the anode potential. Yeah, so he tried to figure out why this is going on. So now let's look at the simple band structure, right? The simplest band structure to understand what thermionic emission is. So you can draw it like this, where this is your vacuum, right? And then you have electrons up to a certain level, which is your Fermi energy. Yeah, this is your conduction band, and the potential energy difference, or the energy difference between the top of the conduction band and the vacuum is the work function that is necessary for an electron to escape. Correct? And the assumption here is that the electron sees a vertical potential difference. So the vacuum is completely at a much higher potential difference than the electron in the metal itself, right? So there's always an abrupt change that the electron in the metal experiences. But in reality, that's not the case. So let's just take a look at what goes on the surface of the metal. So let's assume that this is the metal surface. And an electron which was located at a certain position here, right? It just was able to escape the surface of the metal, and right now this is where your electron is, right? So when the electron leaves from a particular position, you can think of the loss of the electronic charge, which is negative, right, from the metal, as the gain of a positive charge in the metal itself. So now if you go by the simple electrostatics, you have a negatively charged particle which is at a distance z from the surface of the metal. That means at a distance, let's say negative z, you have a positively charged entity, right? So as a consequence of that, the electron experiences an electrostatic attractive potential which can be expressed as V as a function of z, that's the distance from the surface of the metal, is 16 pi epsilon c, right? So this equation comes directly from electrostatics, and if you are unable to understand this, I'm assuming you have some background in electrostatics, but if you're unable to understand that, please talk to me and I can walk you through how we can get this from two charges that are at a distance 2z from each other. Okay, so, and also the negative sign over here, the negative sign is associated with a attractive potential. That's just the convention. A positive sign would mean repulsion. Okay, so the effective potential that the emitted electron experiences can be written as, which is as a function of z. That's the term we saw in the previous equation, and this is the work function, right? So in the original picture of the band diagram, we had an abrupt change, right? So that's your abrupt change, and then you have your Fermi level, you have your conduction band, and that's your work function, vacuum. Right? But now if you apply a potential in the anode, the diagram changes a bit. So the original diagram is like this. In this case, there is no anode potential, so your U is equal to 0. But now if you apply a potential to the anode, then let's look at it like this. Because the electron experiences a negative pull from the positive entity inside the metal, the band diagram is not abrupt anymore, but it sort of modifies into a more gradual change. Okay, so this, let's call that 1, and I'm going to describe what that is. And then if you have an additional potential that is applied to the electrode or the anode, this further changes. So let's call that 2, right? So let's just relabel this. This is your Fermi energy, that's your conduction band, and this is your work function. Okay, so instead of seeing an abrupt change, the electron sees a slight difference in the potential. So number 1 is when it is just because of the image charge in the metal. So that's just the attractive pull that the emitted electron sees. And then instead of an abrupt potential difference, the electron, as a consequence of that attractive pull, sees a gradual difference. And now if you apply a potential to the anode, so now if you have the combined effect of the image charge plus the anode potential, you are in principle altering the potential that the emitted electron sees, right? So you're basically changing the band diagram by applying a voltage to the anode. Yeah, so let's go on to the next page. Oops, let's figure this out. Right, so if let's say you apply a voltage V was applied to the anode, right? So as a consequence, the emitted electron at a distance z from the surface of the metal will have a potential V of the electron as a function of z, which is negative EV times z. That's the distance, right? Again, the negative sign is due to attraction, right? Right? So let's figure out what the total potential of the electron is. So the total potential is V, which is a sum of the two potentials we have been discussing about, which is given by minus 1 over 16 pi epsilon naught z, right? And this is E square minus EV dot z, right? And both are attractive forces, so both are negative. And so now if you differentiate, so if we take dV dz and equate that to 0, we will be able to identify the distance z from the surface of the metal where the electron experiences no force, right? So if you do the differentiation, you get Zm, which is E over 16 pi epsilon naught b to the power half. Okay. This can also be interpreted as at Zm, the electron sees the maximum potential before or during the tunneling process. So if we were to redraw the band diagram, so instead of the abrupt change, I'll just draw this for reference sake. You have something that looks like this, and so this point is referred to as the Vmax, which occurs at Zm distance from the surface of the metal, right? So you have your Fermi energy, that's your conduction band, that's your work function, and this is vacuum, which is associated with 0. Correct? Now this distance is typically in the order of few nanometers. Okay, so now if you substitute, so let's just go back here and call this equation 1, and let's call this equation 2. So if you substitute equation 2 in equation 1, right, you will get the magnitude of the potential, or the maximum potential, which is negative V eq 4 pi epsilon naught to the power half. Okay, let's call that equation 3. Right? So the whole idea of doing this math is to look at this quantum tunneling, so to speak, quantum tunneling in a classical picture, right? If you were to look at the same problem from a quantum mechanics point of view, you would be solving for um, wave functions, and you'll be solving the Schrödinger equation, and how the wave function is able to transmit through the barrier and things like that. But we are not going to talk about it because it's beyond the scope of this work, of this course. But if you are interested, just we can talk about it offline. Okay. So the whole idea is that the moment you apply an anode potential, right, on a very sharp tip of metal, this promotes quantum tunneling by the process of diminishing and narrowing the barrier height that the thermodynamically emitted electron would see. Okay, so let's get back to the slides. So as I said, you are able to change. So let's look at this. You're able to change the band diagram itself by applying a potential to the anode, right? And then there are different ways to control the work function itself. So there are three types of field emission guns. One is a Schottky emitter, and we spoke about this in the previous calculation that we did, which is a combination of using the thermodynamic emission along with an increase in the potential that is applied to the anode, that is applied to the tip to extract these electrons via a combination of thermodynamic emission and quantum tunneling. The cold field emitter simply uses the field, so there is no temperature involved, unlike the Schottky emitter. The basic difference between the Schottky the Schottky emitter and the thermal field emitter is that in the Schottky emitter you create what is called a Schottky junction. That means on top of the tungsten filament you have a coating of zirconium oxide. So zirconium oxide is a semiconductor, and if you bring a semiconductor and a tungsten filament together, or a metal together, you create these junctions called Schottky junctions. And as a result of that, the work function, the effective work function of the combination of the semiconductor and the metal is less than the work function of the metal itself, right? So you're able to reduce the work function, which means now you have better probability of the quantum tunneling happening along with the thermodynamic emission. But in case of a thermal emitter, it's brute force. You're applying a high field with some thermal energy to get the knock off the electrons of the metal. Okay. The Schottky emitters are really good in terms of lifetime. They are always on because you don't want to contaminate the zirconium oxide, simply because it's a field-driven process. The way to clean an emitter if it is contaminated is to flash it, which means you apply a very high voltage to the emitter and hope that it burns off any contamination on the surface. Okay, so since emission of electron depends on the work function of the tip, it is very, very important that you keep the tip clean. There shouldn't be any oxide formation on the surface of the tungsten itself. So if you have tungsten and if there is some oxygen in the electron column, then you can end up getting some kind of an oxide on the surface, which is not good. Okay, so let's take a look at the gun assembly in case of a field emitter. You have the tip, right? From where you're getting these emitted electrons. And then there are two sets of anodes. The first anode is the potential that you apply to the tip. So when I was talking about the anode potential um, in the mathematical discussion, that was between the tip and the first anode, right? So this anode is the electric field. The potential at this anode is the electric field that the electron sees in order for it to escape the tip. So that is a field emission that happens. And the second anode is the conventional anode that we also saw in case of the thermionic gun assembly. This second anode is there to generate the acceleration so that the electron is able to move at a given kilo electron volts depending on what potential or voltage you apply to the second anode. Okay, so typically these field emission sources are single crystals that are etched into very, very small tip diameters or radii of about 100 nanometer. Depending on the crystal orientation of the tungsten, there are certain variations in the work function. So it has been seen that if you are able to cut the tungsten into the direction of 310, that results in a lower work function. So that is something that people do all the time. The first anode is is responsible for the field emission itself. So that's in the order of 3 to 5 kilovolts. And the second anode is the one for acceleration, which is between 20 to 200 kilovolts. Right? So if you apply that kind of an energy, potential to a tip of about 100 nanometers in radius, you end up getting a tremendous field strength in 10 to the 7 volts per centimeter, right? So the emission current is in the order of 5 microamps. So you can work out the current density, which is basically the emission current divided by the area of the tip. And the current density is in the order of 10 to the 5 ampere per centimeter square. If you compare that to tungsten, it is orders of magnitude different, right? So tungsten is significantly lower in terms of the current density. Okay, so now if you look at the equation for maximum brightness, which is the current density times electron charge times the accelerating potential over the energy spread. Now because it's a cold emission gun, the energy spread is relatively very low. It is about 0.3 electron volts. And just for perspective, in the thermionic emission guns, we saw this number to be about 2.5 electron volts, right? So this is about 10 times less in terms of the energy spread. Immediately tells you that the quality of the emitted electrons or the electron beam is really good. So just plug in those numbers and find out what is the brightness at an acceleration of about 20 kilovolts. Okay, so that's the end of this lecture.